Okay, now we're going to go on and actually do some derivations. In particular, we're going to derive an equation that relates position, time, and acceleration. This is only for constant acceleration though, and this is something I want to stress. So the equations that we're about to derive are what we call the kinematics equations. So kinematics is physics that relates to motion. But this is only true in the case that we have constant acceleration. Now that's normally going to be true, but I could give you a situation where acceleration is not constant. So please keep in mind, this is only valid for constant acceleration. And anytime you're looking at a physics scenario, you should ask yourself, is constant acceleration a reasonable model to use? Now the other thing I want to mention is this is for one dimension. I'm using here the subscript of x, but instead this could be all y. So the fact that these subscripts are the same is very important, but this could either be x or it could be y, and so usually the book will give it to you with a subscript of s representing a generalized coordinate. So the first step is that we're going to look at just velocity, not yet position. And we've said that velocity at some final time, so I could write this as v subscript fx, is going to be equal to our initial velocity plus our integral of acceleration, and this is really just the definition. So this is always true, regardless of whether you have constant acceleration or not. However, because we do in fact have a constant acceleration, right? This is just constant, that what you hopefully recognize is that if I'm integrating something that doesn't depend on t over dt, all I have to do is multiply this acceleration value by tf minus t initial, which is what delta t is. This represents tf minus t initial. So there you go. That our final velocity, and again we could write this as just v of f of x, is going to be equal to our initial velocity plus acceleration times delta time. Nice. So now, what if we want position? Now notice that there's a nice analogy between these two equations, that now we have position is related to initial position plus the integral of velocity, where up here we had velocity is equal to initial velocity plus integral of acceleration. So now we want to find position. So initial position is just whatever the value is in that problem, but now we need velocity as a function of time. So one mistake would be to assume that velocity is constant. Velocity isn't constant. We have acceleration. However, what we can do is effectively use this piece of information. And I'm going to do this in kind of a careful mathematical way, notationally, but the idea is just that we're plugging this in there. So we have to be a little bit careful of notation, but overall that's the basic idea. So one of the differences that I'm going to use is instead of saying Vx of final time, I'm just going to use general time, so that this is a function of t rather than a specific t. And one of the ways that I can do that is instead of using delta t, where that typically represents final minus initial, I'm going to use instead just t, where again that's generalized time, minus initial time. So hopefully that's clear. I'm using effectively this answer in here, but I'm changing my notation a little bit so it's clear that my velocity is a function of time in general. So now, as I plug that in, all I've done is literally put this in. We now need to start actually doing some math. Now this isn't that hard of an integral, but I know that some of you might be somewhat new to integration, or maybe it's been some time since you've seen the integration. So I'm going to try to do it out in a few steps to really make it clear what the process is and hopefully help remind you of what some of the math steps are. So this might actually seem more complicated than necessary since I'm actually showing all of these steps. So the first thing that I'm going to do is break it into pieces. So I have two terms in my integral here, and I can effectively create each of them into their own integral. And the reason I'm going to do this is I want to really focus separately on each of these terms to think about what depends on time and what does not. So I have this initial velocity term that's going to have its own integral, and I have this acceleration term that has its own integral. Now note that the integral bounds are time initial to time final because I'm finding this final position. Obviously, you could do this a little bit differently if you want x as a function of time, but hopefully it's clear that that would just be changing this specific final time to just a generalized t in your integral. So now I have these two separate terms and I can think about them separately. Now, I need to go on to the next page soon, so don't worry too much, but we're going to just have this equation again on the next page. So when I look at this first integral term, I remember that this velocity is actually a constant. It doesn't depend on time. Now be careful, because this isn't the velocity as a function of time, which is not constant. It is specifically the initial velocity. This is why these subscripts are really important. If I just wrote this as v, it would seem that our velocity is changing in time. But because this is v initial, well, our initial point is fixed. So this is one specific value. Now again, we're in the position of only talking about constant acceleration, which means that this acceleration term here is also constant by definition. So up until this step, this is general for any acceleration, but the next step is only in fact going to be true for constant acceleration. What I'm going to do is pull this velocity outside of the integral because it's constant, and similarly I can pull this acceleration outside of the integral because it's constant. Don't do that if it isn't constant. So now I'm left with some integrals, which hopefully aren't going to be too hard to do. The one thing that I am going to do a little bit differently is think about this. And again, depending on how comfortable you are with integration, you might glance at this and know what the answer is. But what's a little bit confusing is that I have a t final, a t initial, and a t. So there's a few different approaches here, and I'm going to take the approach of actually transforming this so that hopefully we can see more clearly what this integral is going to look like. And what I've done here, you can see what the answer is on the next line, but I've just done the transformation that tau, which is the Greek letter corresponding to t, so it looks like a little t, is equal to t minus t initial. Now, when I do that, I can say that d tau is then just equal to dt, since t initial is a constant, and then I can change my bounds of integration to get that when t is equal to t initial, tau is equal to 0. When t is equal to t final, then tau is equal to t final minus t initial. So I've just done a change of notation here, which is one approach to this, to hopefully make it clear what this integral is going to do. Now, if you've noticed, I've already done out the first integral, since the integral of dt is just going to be equal to t, and I've then evaluated that of t final minus t initial. Hence, I have that here. And again, be careful that you might have a problem where t initial equals 0, so you don't have to worry too much about it. But oftentimes we don't have an initial time equal to 0, especially if you're talking about different pieces of the motion. So please be careful about that and keep track of those limits of integration. So now I have an integral here that looks a little more clear. And when I do that out, I get that the integral of tau d tau is 1/2 tau squared. And now I evaluate that from 0 to t final minus t initial. And again, there are different approaches to doing this integral, and if you feel like this isn't clear or you would have wanted to do it a different way, feel free to try the integral your way and verify that you get the same answer. So now I need to plug in that t final minus t initial into tau squared. Obviously, when we plug in 0, we get 0 there. And so now I'm just showing kind of two equivalent forms here. So this looks long, but note that there's really just two forms to this equation. We have form number 1 and we have form number 2. And the only difference between these two forms is that in form number 1, I'm explicitly saying t final minus t initial, and in form 2, I explicitly say delta t. So delta t is equal to t final minus initial, so these are really just two ways of saying exactly the same thing. So there you go. This is now a very important equation, which is our equation for final position in terms of initial position, initial velocity, the elapsed time, and a constant acceleration. So this is a really important equation that you will use a lot. It is, again, only true when you have constant acceleration, and it's important to note that this is all in one dimension. So everything here is about x. Okay, I know that that derivation was possibly very complicated, or perhaps might seem like a lot of work, and it isn't that I want you to memorize this. I'm not even going to ask you to do a derivation like this from memory on a test or homework or anything like that. What's most important is the process. We started with something that we knew, and then we used a mathematical method to get to a new piece of information. So this is really important for problem solving. So what I want you to be able to do is go through those sorts of mathematical steps where you're just using calculus and using algebra as a tool. But really, what's most important here is the physics of how you actually interpret those equations and apply them to situations. So I know you might be feeling a bit wiped out after that, but what I would encourage you to do is perhaps go back, watch that again if you didn't quite follow it the first time. The book, of course, goes through the derivation as well, and try doing it out on your own. If you feel like it makes sense to maybe skip certain steps or do the integral a different way, try that as well. So next we're actually going to do another derivation that's really similar to this one, and again is going to be generating an equation that's going to be really useful.